Good morning. So today we're going to discuss new module electrochemistry. So in electrochemistry we're going to discuss electrochemical cells. So electrochemistry is the branch of chemistry which deals with electrochemical cells, especially redox reactions. So most of you might have studied this electrochemistry in your +1 or +2. So electrochemistry, as discussed, as I told earlier, it's a branch of chemistry where it involves the loss, that is oxidation and reduction, losing of electrons or gaining of electrons. So electrochemistry mainly depends upon electrochemical cells. So now in today's discussion, let us see what are these electrochemical cells, what is oxidation, what is reduction, and few terms, what is free energy, what is entropy. Right, so let us discuss one by one. Electrochemical cells are devices which convert electrical energy into chemical energy or chemical energy into electrical energy. I repeat, electrochemical cells are the devices which convert chemical energy into electrical energy or electrical energy into chemical energy. It can also be told as the cells which convert or the devices which convert chemical energy into electrical energy and vice versa. There are mainly two types of galvanic electrochemical cells, and they are galvanic cells and electrolytic cells. So galvanic cells are the devices which convert chemical energy into electrical energy, and whereas electrolytic cells are the devices which, by virtue of chemical energy or by virtue of electrical energy, some electrical changes are brought about. So the best example for galvanic cell is the Daniell cell, and the best example for electrolytic cell is electrolytic process or electrolysis process. In galvanic cell, what is galvanic cell? It is a device where chemical energy is converted into electrical energy. So in galvanic cell, anode is negative, cathode is positive. The example is Daniell cell. Electrolytic cell is a device by virtue of electrical energy, some chemical changes are brought about. For example, if we consider electrolysis process, so we'll have an anode, we'll have a cathode. So anode will be impure metal, cathode will be pure metal. So when you pass the current, what happens? Electrolysis takes place and the impure it is present in the anode will get settled at the bottom of the anode called as anode mud. The pure metal will move towards the cathode. So when will this occur? Only when you pass the electric current. So when you pass the current, some chemical changes occurs. So this is called as electrolytic cell. So the galvanic cell example, Daniell cell, and electrolytic cell example are electrolysis process. We're not going to discuss much about the electrolytic cell in our discussion. We're going to deal only about galvanic cell. So in this module and also in the next module, we have only galvanic cells, the reactions concerning galvanic cell. Okay, so as discussed, so these are the differences. Okay, so reactions in galvanic cells are spontaneous, whereas the electrolytic cell is non-spontaneous. So the best example for galvanic cell, as discussed, it is Daniell cell. What is Daniell cell? So Daniell cell is a cell where Daniell cell contains zinc electrode dipped in zinc sulfate, copper electrode dipped in copper sulfate solution. So these both are connected through a salt bridge and to maintain electrical neutrality. So zinc dipped in zinc sulfate solution, copper dipped in copper sulfate solution, where these solutions are connected through the salt bridge. A zinc electrode and copper electrode connected through the voltmeter. So now zinc dipped in zinc sulfate forms a half cell, copper dipped in copper sulfate forms another half cell. So any metal dipped in its own salt solution, acts as a half cell. Any metal dipped in its own salt solution acts as a half cell. So we have two half cells here in your Daniell cell. One is zinc half cell, other one is copper half cell. So zinc half cell is connected to copper half cell through salt bridge and connected to voltmeter. The salt bridge is there in order to maintain electrical neutrality. Right. So now what happens when zinc is dipped in zinc sulfate? When zinc is dipped in zinc sulfate solution. At zinc undergoes oxidation. At zinc undergoes oxidation to give 2 electrons. Zinc undergoes oxidation to liberate 2 electrons. Zinc will undergoes oxidation to give you Zn2 plus 2 electrons. So at copper undergoes reduction. So these electrons will move towards, from here it will move, from zinc it will move towards the cathode, okay, and it will come towards the cathode. So here what will happen is copper Cu2 plus, so Cu2 plus will accept 2 electrons. Cu2 plus will accept 2 electrons to give Cu. Cu2 plus will accept 2 electrons to give Cu. So now here at zinc oxidation occurs and at copper reduction occurs. So zinc will donate 2 electrons. At zinc will undergo oxidation. So zinc will give 2 electrons to form Zn2 plus. So these electrons will move towards the copper, and here in copper sulfate, copper in the form of Cu2 plus and SO4 2 minus. This Cu2 plus will accept the 2 electrons and get reduced to Cu. So loss of electrons, zinc is losing 2 electrons. So loss of electrons is called as oxidation, gain of electrons is called as reduction. So loss of electrons is called as oxidation, gain of electrons is called as reduction. Okay, so now as per IUPAC, the electrode where oxidation occurs is termed as anode, and the electrode where reduction occurs is termed as cathode. The electrode. So here at zinc oxidation is occurring. So zinc is losing 2 electrons. So loss of electrons is called as oxidation. So at zinc electrode 2 electrons are lost, right? So this is called as anode. At copper 2 electrons are accepted. So this is called as cathode. So as per IUPAC, the electrode where oxidation occurs, it is named as anode, and the electrode where reduction occurs is termed as cathode. So now the question is, what is the charge of anode and cathode? So as per IUPAC, so anode is negatively charged and cathode is positively charged. So this can be also be represented. So the representation is given here. So this cell, this salt bridge, whatever salt bridge you have here, this salt bridge is written by 2 vertical lines. Can you see here? So left hand side you are going to write the anode, right hand side you are going to write the cathode. So what is the anodic reaction? Zn is giving Zn2 plus. So write Zn here. So instead of arrow mark, put a slash and write ZnSO4 or Zn2 plus. So here what you have, Cu2 plus, write Cu2 plus or write the electrolyte here, it is cathode. Instead of arrow mark, put a slash and write Cu. So you can write the Zn sulfate, zinc sulfate solution itself or the metal ions whichever it is donating. Right. So in the cell can be represented as, the salt bridge is given as what? We're going to write the salt bridge as 2 vertical line. Left hand side we're going to write the anode, right hand side we're going to write the cathode. Okay. This is how the cell is represented. So whenever a metal is given, so some potential is developed. So how the potential is developed? So whenever a metal is dipped in its own salt solution, so what happens? It is having a natural tendency to either lose electron or gain electron. So due to this, the metal gains some potential. This potential is called as electrode potential. I'll just explain. So we have zinc here. You're taking zinc here. So zinc is dipped in zinc sulfate solution. Okay, this is zinc and this is zinc sulfate solution. So what will happen? So Zn will donate, lose electrons to give you Zn2 plus and 2 electrons. So what happens here? These electrons will be on the surface of the electrode because it is not connected to anything, right? So whereas the Zn2 plus will be inside the solution. So these negative charges will attract the positive charges. These negative charges will attract the positive charges. So what will happen? It should get neutralized, but it is not getting neutralized. It should get neutralized, but it is not getting neutralized. So this negative and positive charges will be on the surface. It will be on the metal solution interface. So due to that, it will develop some force of attraction. It will develop some force of attraction, okay, giving rise to the electrode overall potential. If you take north pole and south pole of the magnet, what will happen? It will get attracted. You can feel that if you take north pole and north pole, it will what? Move away, right? So you can feel the force, that magnetic field. Similarly here, negative and positive signs will attract that force. So the overall force gives some potential to the electrode, that is called as electrode potential. So if the same electrode potential is measured at some standard temperature and pressure and at 1 molar concentration of the solution here, then it is called as standard electrode potential. Okay, so now let us see, there are few terms involved here: energy, free energy, and entropy. So any energy is a substance associated with definite amount of energy. So which might be internal energy or it might be external energy. So any energy which can be converted into usable form of work is known as free energy. So what is entropy? So entropy is randomness or disorderliness of the system. So you know that solid ice, from solid to liquid, entropy increases. From liquid to gas, entropy will increase. So this will be understood better. The entropy concept will be understood better in the video which we play here now. So this here you will understand the entropy video better. What is entropy? The concept of entropy will understood better here.
There's a concept that's crucial to chemistry and physics. It helps explain why physical processes go one way and not the other. Why ice melts, why cream spreads in coffee, why air leaks out of a punctured tire. It's entropy, and it's notoriously difficult to wrap our heads around. Entropy is often described as a measurement of disorder. That's a convenient image, but it's unfortunately misleading. For example, which is more disordered, a cup of crushed ice or a glass of room temperature water? Most people would say the ice, but that actually has lower entropy. So here's another way of thinking about it, through probability. This may be trickier to understand, but take the time to internalize it, and you'll have a much better understanding of entropy. Consider two small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed in the two solids and still have the same total energy in each. Each of these options is called a microstate. For 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates. Of course, there are other ways our 8 quanta of energy can be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that some of the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates. Entropy is a direct measure of each energy configuration's probability. What we see is that the energy configuration in which the energy is most spread out between the solids has the highest
I think now you
entropy.
better
So, in a general sense,
you understood what is entropy, right? So from solid to liquid, how entropy will change, right? So next discussion will derive a Nernst equation. So how Nernst approach to a Nernst equation, we'll discuss in our next class. Thank you.